variation of acceleration, amplitude, driving force, frequency. Okay. Variation of acceleration, amplitude with driving force, frequency. Variation of acceleration, amplitude with driving force, frequency. Okay. Variation of acceleration, amplitude with a driving force, frequency. Okay. And the driving force given by F equal to F naught cos omega t. Okay. The displacement of the force oscillation in the steady state is given by y equal to F naught upon omega Zm sin omega t minus phi. Okay. This is the displacement of the force oscillation in steady state. Displacement in steady state. Displacement in steady state. Okay. And velocity v equal to set of y equal to dy by dt equal to f naught upon Zm cos omega t minus phi. Okay. Then acceleration, double differentiate of y, okay. Acceleration double differentiate of y equal to d square y upon dt square equal to minus f naught omega by Zm sin omega t minus phi. Okay. Where Zm equal to under root of r square plus omega m minus s by omega whole square. Okay. Then acceleration amplitude. Acceleration amplitude equal to f naught omega upon r square plus omega m minus s by omega square. Okay. Omega square for all to the power 1 upon 2, all to the power n 1 upon 2. Okay. Then this is f naught upon r square by omega square plus m minus s by omega square whole square, that is 1 by 2. Okay. Now three cases arises. Now three cases arises. Now three cases arises. First is at low frequency. Okay. At low frequency, omega tends to 0. Therefore the term s by omega square dominates, provided omega square dominates, provided r is small. S by omega square dominates, provided r is small. Okay. In such a case, the oscillator is said to be stiffness controlled. Okay? In such a case, in such a case, the oscillator is said to be the oscillator is said to be stiffness controlled. Stiffness controlled. Okay, when r is small and omega is tends to 0, then Zm equal to s by omega and acceleration amplitude. Okay, when r is small, r is small, when r is small and omega tends to 0, and omega tends to 0, and Zm equal to s by omega and hence acceleration amplitude, and hence acceleration amplitude, acceleration amplitude equal to f naught omega by s by omega, that is f naught omega square by s, but omega tends to 0, okay, omega tends to 0, okay. Hence, acceleration amplitude is 0. Acceleration amplitude is 0, okay. Second point, at high frequency, at high frequency, when variation of acceleration amplitude with driving force frequency. When the driving force is given by F equal to F naught cos omega t, and the displacement of the force oscillator in steady state is given by y equal to F naught upon omega Zm sin omega t minus phi, and velocity v equal to differentiate of y, that is differentiate of displacement, and then the differentiate of displacement y dy by dt equal to f naught upon Zm cos omega t minus phi, okay. The differentiate of sine is cos, so then sin omega t minus phi is cos omega t minus phi, and omega t minus phi, differentiate of omega t minus phi equal to omega is outer, and this omega is cancelled out by this omega, then dy by dt equal to f naught upon Zm cos omega t minus phi, okay. And acceleration equal to double differentiate of displacement, that is d square y by dt square, then dy by dt single differentiate equal to that, and after double differentiate of y displacement, equal to d square y upon dt square, that is minus f naught omega upon Zm sin omega t minus phi. This is the acceleration, where Zm equal to under root of r square plus omega m minus s by omega square. Acceleration amplitude. equal to f naught omega whole upon r square plus omega m minus s by omega whole square whole to the power 1 by 2. Okay, this is the value of under root zm, value of zm. Okay, and equal to f naught upon r square by omega square. Omega square is common and omega is common and cancel out by this omega. Okay, then f naught upon r square upon omega square plus in bracket m minus s by omega square whole to the power 1 by 2. Okay, now three cases arises. At low frequency, omega is tends to 0, therefore the term s square by omega square dominates provided r is small. Okay, r is small. In such a case, oscillator is said to be stiffness controlled. Okay, and when the r is small and omega tends to 0, then Zm equal to s by omega, and acceleration amplitude is f naught omega by s by omega, and f naught omega square by s, and but omega tends to 0, hence acceleration amplitude is 0. Hence acceleration amplitude is 0. Okay, acceleration amplitude is 0. Omega tends to 0, then hence acceleration amplitude is 0. Okay, and at high frequency, for a large value of omega, for large value of omega, okay, for large value of omega, s by omega can be neglected as compared to omega, can be neglected because the value of omega is very high. Okay, then s by omega can be neglected because omega is denominator. S by omega neglected, and r square is compared to omega square m square, so that we get and r square as compared to omega square m square, so that we get Zm equal to omega m. Okay, omega m. In such a case, the oscillator is said to be inertia controlled. In such a case, the oscillator is said to be inertia controlled. The oscillator is said to be inertia controlled. Okay, inertia controlled. Then for large frequency acceleration amplitude, for large frequencies, acceleration amplitude is 0. Acceleration amplitude is 0. Sorry, for large frequencies acceleration amplitude is f naught omega by Zm, f naught omega by Zm, f naught omega by Zm, that is f naught omega by omega m, that is f naught by m, f naught by m. Okay. The acceleration amplitude depends upon is that the acceleration amplitude depends upon the driving force F naught and mass m, but is independent upon frequency, independent of frequency. Okay. The acceleration amplitude depends upon the driving force F naught and mass, but independent of frequency. Okay. Next point, maximum value of acceleration amplitude. Maximum value of acceleration amplitude. Okay. Maximum value of acceleration amplitude. Maximum value of acceleration amplitude. Okay. Maximum value of acceleration amplitude. Okay. The acceleration amplitude becomes maximum when omega by Zm is minimum, or Zm by omega is maximum. Okay. The acceleration amplitude becomes maximum when omega by Zm is a minimum, or Zm by omega is a maximum, Okay. Is a maximum, is that d by d omega in bracket Zm omega inverse equal to d by d omega inverse r square plus omega m minus s by omega whole square, that is 1 by 2. Okay. Then this is d by d omega r square by omega square plus m minus s by omega square whole to the power 1 by 2. That is 1 by 2 r square by omega square plus m minus s by omega square whole square, that is minus 1 by 2. And minus 2 r square by omega cube plus 2 m minus s by omega omega square and 2s by omega q. Okay. D by d omega r square by omega square plus m minus s by omega square whole square 1 to the power 1 by 2. Okay. And this is 1 by 2 r square by omega square plus m minus s by omega square whole square to the power minus 1 by 2, and in another bracket minus 2 r square by omega q plus 2 m minus s by omega square into 2s by omega q. Okay. That is minus r square by omega q plus 2sm by omega q minus 2s square by omega to the power 5 whole upon r square by omega square plus m minus s by omega square whole square, that is 1 by 2 is equal to 0. Okay. Minus r square by omega q plus 2sm by omega q minus 2s square by omega to the power 5 equal to 0. That is r minus r square plus 2sm minus 2s square by omega square equal to 0. Okay. And 2sm minus r square equal to 2s square by omega square. Then omega square equal to 2s square by 2sm minus r square. Then omega equal to under root of 2s square upon 2sm minus r square. Thus the acceleration amplitude is maximum when omega equal to under root of 2s square upon 2sm minus r square. Taking this value of omega, taking this value of omega as omega dash, we have maximum acceleration amplitude. Equal to f naught omega dash whole upon r square plus omega dash m minus s by omega dash whole square whole to the power 1 by 2. Okay. Then r itna and the omega equal to under root of 2s square upon 2sm minus r square. Okay. And thus the acceleration amplitude is maximum when omega equal to sm square upon 2sm minus r square. Taking this value of omega is omega dash, we have maximum acceleration amplitude is f naught omega dash whole upon r square plus omega dash m minus s by omega dash whole square whole to the power 1 by 2. Okay, point A. Point A. 1 minute. Point A is maximum oscillation amplitude at high frequency. Maximum acceleration amplitude at a high frequency, okay. The acceleration amplitude at high frequency, at a high frequency. The acceleration amplitude equal to f naught omega by Zm. F naught omega by Zm, where Zm equal to under root of r square plus omega m minus s by omega whole square. Okay, for large value of omega, large value of omega, s by omega can be neglected as compared to omega m. R square as compared to omega square m square, and we get Zm equal to omega m. For large frequencies, maximum oscillation amplitude. For large frequencies, maximum acceleration amplitude, maximum acceleration amplitude equal to f naught omega by Zm equal to f naught m by omega m equal to f naught by m. Okay, is that the maximum acceleration, the maximum acceleration amplitude depends upon the driving force, and the mass m, but is independent of frequency. Okay, the maximum acceleration amplitude depends upon the driving force and the mass m, but independent upon frequency. B point. When damping constant is very small, when damping constant is very small, the acceleration amplitude, the acceleration amplitude resonance resonance frequency is omega dash equal to under root of 2s square by 2sm minus r square. When damping constant r is very small, when damping constant r is very small, when damping constant r is very small, then r square can be neglected as compared to 2sm, and we get omega dash equal to under root of 2s square by 2sm, that is under root of s by m. Natural frequency of forced oscillator. Natural frequency of a forced oscillator. Natural frequency of forced oscillator. Hence, when damping is very small, the acceleration amplitude resonance frequency equals the natural frequency equals the natural frequency. Okay, natural frequency of the forced oscillator, frequency of the forced oscillation. Okay, forced oscillator. Okay. Hence, when the damping is very small, the acceleration amplitude resonance frequency equals the natural frequency of the forced oscillator. Okay, thanks. Next is sharpness of resonance.